Recall from yesterday's lesson, we took a look at exponential growth. Now, that's where our equation was continually growing because our growth ratio, our value for b, was greater than 1. Well, today we're going to take a look at the case for exponential decay. So we have the same function here, y equals a, our initial amount, times b, our growth ratio, to the exponent of x. Now, the difference today is our exponential decay is going to have a value for b that's going to be between 0 and 1. So our growth factor here is going to be some fraction or some decimal that's positive in value, but between 0 and 1. Anytime we multiply something by a number less than 1, it will be decreasing or decaying in value. So let's take a look at a few examples here. It says, suppose a new piano costs $8,500 and it depreciates 6% each year. Now, depreciation is just another way of saying decreasing in value at a constant rate. So it's depreciating at 6% each year. We want to write an equation that gives the piano's value in t years. So we'll start off by listing the original value. This is the initial amount, our value for a. And now we're going to multiply it by our growth ratio here, or actually our decay ratio. So notice that it depreciates by 6% each year. Now, percent needs to be changed to a decimal, so it's 1.06. However, we're decreasing that much each year. So we have to take our initial value, which is 1, minus 0.06. And now that's my growth ratio, which we'll simplify here in just a second, to the t power. So the value in t years can be given by this expression, 8,500 times 0.94 to the t power. Now again, this 0.94 represents 94%. So if it's losing 6% each year because it's depreciating, then it's retaining 94% of its original value. So you can see our growth ratio here is 0.94, which is less than 1, and this will give us the piano's value t years later. So let's find the value after 5 years. The value 5 years would be 8,500 times 0.94 to the 5th power. We plug that into our calculators. Our calculator will give us that value of $6,238.18. So you can see it's already lost quite a significant amount of value in just 5 years. All right, Morgan and Chris buy a car for $1,800. Its value decreases by 12% a year, so again, it's depreciating. Write a formula for the value of the car t years after they buy it. So same thing here. After t years, it's going to be the original amount. Now it's going to be 1 minus their 12% here, so I'm going to write that out up here. 1 minus 0.12 is going to give me 0.88. So if it's losing 12% of its value, then it's retaining 88% of its value. And then our exponent here is our variable t. So find the value again in 5 years. So a of 5 here is my 1,800 times 0.88 to the 5th power. And when we punch that into our calculator, we get $9,499.17. So again, in 5 years, you've lost half the value of your car almost. All right, now here's an example. Example 3 gets into this idea of half-life. And half-life is simply the time period it takes for a substance to decay to half its original amount. So we have strontium-90 has a half-life of 29 years. This means that each 29-year period, the half of the strontium-90 will decay and half will remain. So it says, suppose you start off with 1,000 grams. How many grams of strontium-90 will you have after 6 half-life periods? So we're going to start off with our 1,000, which is our initial amount. And our growth factor for half-life is always 0.5, or 1/2. And we're going to raise that to the 6th power. So this will give us how much we have left after 6 half-life periods, and that number comes out to be 15.625 grams. All right, next it wants us to find how many years are actually in 6 half-life periods. So if each period contains 29 years and there's 6 of them. We'll take 6 times 29, and that comes out to be 174 years. All right, part C wants us to write a recursive formula for A sub n, the number of grams of strontium-90 that remain after n half-life periods. So let's start off with our recursive formula. Our initial amount will be our first term here, and that initial amount is 1,000. Now notice that my subscript is 0 and not 1, because n represents the number of half-life periods. So A sub 0 would be my initial amount before I even take one half-life. So A sub n, my formula now, will be my half, which is my constant growth ratio here, times A sub n minus 1. And this is going to be for all those values where n is greater than or equal to 1. Now remember here, we're starting at 1 because we only have our initial value, and we want to find our first term, starting at our first term, second, third, and fourth. Okay, next it says now to write an explicit formula for A sub n, and again keep in mind n is the number of half-life periods. So let's write it as A sub n is equal to, now it's going to be our initial amount, 1,000, times 1/2 to the nth power. And this is going to be for all values of n greater than or equal to 1 as well. So we're going to start here at the first term, where we'll take 1,000 and raise it and multiply it to 1/2 to the first power, which will give us our first term of 500 grams. All right, finally here it says to write a formula for the amount remaining after any real number of half-life periods. So I'm going to come back up here to the top here, and that amount remaining after t half-life periods is simply 1,000, our initial amount, times 1/2 to the t power. All right, one more example here for today. We got carbon-14, sometimes known as this, I don't know what that means, has a half-life period of 5,730 years. Man, that's old. That's like as old as me. This means that 5,730 year period, half of the carbon decays and becomes nitrogen, while half remains. All right, so it says a sample began with 80% pure carbon. Write an equation for the percent of carbon-14 remaining in the original sample, x half-life periods. So we're going to start off with the amount remaining, where x is our number of half-life periods, is equal to the amount that we have, 80 now here, this is going to represent percent, times 1/2 our growth factor for half-life period problems, to the x power. So there it is. It says now to use decimals to graph your equation in part A, and use it to find the age to the nearest century of the sample that contains 60% of its original carbon. All right, well, I've graphed that function over here on decimals. You can see our f of x is equal to 80% to the 1/2 to the x. So when does that f of x come to 60% here? So we're going to take a look at our table of values, and you can see over here our table of values starts off with -2, -1, 0, our initial amount here. And if we go by tenths, you see that we have 0.1, 0.2, 0.3. Right here at 0.4, our f of x, or the percent that we have remaining, is 60%. So that means when x is equal to 0.4, or in other words, 0.4 of 5,730 years, then that's when that's how many years it would take for that carbon dating to get down to 60%. So we need to multiply 0.4 times 5,730, and that's going to give us the number of years of 2,292 years. In other words, that sample will be 2,292 years old.